remember we after this we're going to talk about the last chapter we talk about is chapter 8, which we have a homework, okay? And because the time is really kind of short, there's not many homework. There's only like 6 problems or something, and some of them are just like basically multiple choice questions. So it shouldn't take you long to do it. It's a small chapter for us. I don't want to make it too heavy for you guys because we're going towards the end. So, but you still need to do the homework, and so the chapter 8 will be tested on the final, okay? So chapter 8 will be on the final, okay? And so this part is going to be, I mean, all the previous chapters has been tested, and so only this chapter is totally new on the final. So yeah, we'll talk about what to include in this chapter, but basically it's a short chapter, okay? So we'll talk about final next week, either maybe I think Wednesday is probably a good time to talk about the final because Thursday is final. And if you guys have questions, I can talk about it on Monday as well. Basically Monday or Wednesday, we'll talk about the final exam, okay? Now, as some of you wanted, we'll also talk about chapter 9, and we'll talk about fluid, okay? This is for MCAT exams for some of you, and wait, okay. And then so you guys, but this is not going to be on the test, okay? We don't even have a homework problem, homework for this one, but I'm going to spend some time either Monday or Wednesday to talk about this chapter to kind of help you guys to kind of review, I mean, or do an overview for this for the stuff for this chapter, so that it can be useful for you for the MCAT, okay? So anyway, that's the plan. So I think we have a really good chance to finish chapter 8 in this week, okay? If you have any questions, send me a message, okay? Or ask me. Okay, so now let's move on to chapter 8. Okay, the title says rotational equilibrium and dynamics, okay? As you see here, like torque, and then this part here is the rotational equilibrium and then the dynamics. Well, there's again a lot of stuff in this chapter. This roughly corresponding to, I mean, in terms of logic, it corresponding to Newton's law, chapter 4 Newton's law, chapter 5 energy, and chapter 6 momentum. But we don't have time to cover everything. I mean, mostly because we're going toward the end. I don't want to introduce a whole lot of new concepts with like only 1 week or so toward the end of the semester. So we'll focus on the first part of the chapter, rotational equilibrium. We'll introduce this concept called torque. This will be our last concept to introduce, okay? And we'll cover roughly the first three sections in this chapter. Well, this one here, this is actually more like Newton's law, kind of like Newton's law for rotation. This one's like energy, kind of like chapter 5, and then this one's kind of like a momentum. We won't have time to do these 3 chapters, so 3 sections. So we only focus on the first part of the chapter. Okay, so anyway, this is the plan. Okay, so okay, maybe I'll just write rotational equilibrium. Okay, for chapter 8. Rotation equilibrium. Okay, so what is the problem here? So again, this is certainly related to rotation, right? So when you have something that could do rotation potentially, okay, it's important to consider something to introduce a new concept called torque. Okay, let me show you by this demonstration here. Okay, take this rod here, which is a pencil, right? Now, if you put your fingers underneath it at the right position, it's going to stay balanced horizontal like this, right? No problem. Normally, if this pencil is totally uniform in terms of mass distribution, you put your finger at the middle, right? However, if you put your finger on one side of it, like this side, no matter how much force you give it, you understand this cannot stay balanced horizontally like this, right? Okay. So or like this on this side, right? It just simply cannot. I mean, we all understand it's impossible. You just put your finger here, nothing else. Don't, if you leave this, take this hand away, it's gonna definitely fall. So what happens here is when you take this hand away, right? This pencil will fall like this. So it's gonna do a rotation, okay? So in order to avoid rotation, you have to put your finger somewhere in the middle, like this. Okay, sorry, like this. Like this, right? This works. So it seems like location of the force is important, okay, in this case. And when you have a potential to rotate, okay. Now let's go back to, what is the equilibrium? Let's go back to our chapter 4 to remind ourselves, okay. So normally when we talk about mechanical equilibrium, what we really mean here, something can stay at rest, okay. For example, if you have some objects sitting at rest on this on the table, it is mechanical equilibrium, okay? In this case, as we know, there's gravity going down, there's a normal force going up, and these two forces balance each other. So N minus mg equals to ma, because this is in equilibrium, so this equal to 0. So in general, when something is in mechanical equilibrium, you could say that total force on the object equals to 0, okay? This is like the equilibrium condition. Okay, total force equals 0. When that in that case, when total force equals 0, the acceleration of the object is 0. The object can either stay at rest or going with constant velocity. In both cases, we say the object is in mechanical equilibrium. Okay, so that's what the equilibrium means for us. Or maybe let me put at rest or in constant velocity. Okay, however, for the current case, when we have a rod which can rotate, we see that this condition is not sufficient, okay? For example, if you put your finger underneath here, right, it's gonna provide a force here to the object going upward, like normal force. But it's not gonna stay in equilibrium, okay? It cannot stay like balance here, right? If you put a finger like this, it's gonna fall. It's gonna rotate. It's gonna go like this. So same thing here. It's gonna go like, only if you put it at right position, like somewhere in the middle, okay? Then it can stay at rest, okay? So this actually tells us that there's something else we need to consider, okay, for the rotational equilibrium, okay? Now in chapter 4, we talk about only this situation because all the subjects, object in chapter 4, we have kind of like these kind of blocks or squares. They pretty much don't, there's not like has an extended shape. They don't rotate, they don't turn easily. So what we talk about in chapter 4 was fine, but for some object like this, we need to have some new things coming in, okay? So that new thing is actually what we call torque, okay? Let me, let's see. The concept here is the physical quantity we have is called torque. Now, again, we use a Greek letter for it, okay? This is tau. It's not T, right? When you have T, you have this thing going up on top of this this line here, but in this here, it does not go out. So it's not, so please call it tau, okay? It's a Greek letter, okay? So how do we define the torque, okay? Again, the idea here is we want to introduce this quantity so that it can take into account of the rotation probability, you know, the rotation possibility. So we want to define it such that when you have the torque, you can rotate. When you don't have the torque, you cannot rotate, okay? So the torque basically is like it's a reason for rotation, okay? for rotation. Or you can say it's like, it's kind of like the force, okay? We know force is the reason for motion, right? For motion. When you don't have force, the object either stay at rest or stay with constant velocity, but it cannot change the state of the motion. Well, same thing for rotation. Rotation. In this case, we want to define something similar to force, but we call it torque. Okay, so we want to say this torque is the reason for rotation. Okay, so how do we define it so that it can take into account of this phenomenon? So we'll again, this totally come from intuition, you know, and we'll define it like a. Let me give you the mathematical definition, and then we'll talk about the definition here. Okay, so you can define torque as this. Okay, tau equals to F and D and sine sine theta. Okay, so what is F and D and sine theta? Okay, so when you have something like a rod, let's say for simplicity, let's say you pin the rod on the left hand side. Okay, so this point is fixed, so it can be a hinge or something, so that the whole thing can rotate, but it cannot move altogether. Okay. Now you apply a force to the rod. Okay, let's say you have applied this force F here to the rod. Now you can calculate the torque of this force. Well, it equals the magnitude of the force times the distance from the acting point of the force to the rotational axis, D. So this is the distance we talk about. And then the sine theta, the angle theta here refers to the direction of the force and the direction of this distance, okay? This is an angle theta here, okay? So the torque of a force is given by the force times distance times sine of the angle between these two directions. That's how we define torque, okay? Now let me try to explain why this definition helps us to see that, whether a force can generate a rotation or not, right? Again, this is kind of like intuition, right? So let me take another demonstration here. So this is the lid of my coffee cup. So this thing can rotate. Let's say I fix the center of it, okay? So this thing can rotate like a wheel, right? It kind of like a wheel, right? It can rotate like this, but it cannot move in together. So let's say if I apply a force, can I produce a rotation? Sometimes I can, sometimes I cannot, okay? For example, if I apply force right on the rotational axis, okay, right at the center, okay, I cannot rotate it, okay, if it's right around at the center, okay. Does it make sense to you? Well, it's the same thing. Okay, you can either talk about this like a lid, pinning it at the center, or you can talk about like a door. You want to open the door, like say this is a door, right? You want to open it. You want to generate, in both cases, a rotation, right? Well, there's a hinge here, right? The hinge is on this side here. This produces a rotational axis. If you apply force right at the hinge or right at the rotational axis, certainly you won't be able to rotate them, rotate this or that, right? You can easily try it at home. Push the door at the hinge where the hinge is located. Certainly you cannot produce rotation. In that case, okay, the first case is F at the rotational axis. In this case, what really happens is D equal to 0, okay? There is no distance between the rotational axis and the acting point of the force, okay? So because the force acting right at the rotational axis. So because D is 0, so tau is 0, okay? Tau equals 0 because D equals 0, okay? So that's not very effective. Another thing that's not effective is if you apply a force along this radial direction or along this direction, okay? Say in this case, I try to pull this like this. Will it rotate the hinge, the lid? No, right? Same thing, if you apply a force along this direction, try to pull the door or push the door, you cannot rotate it, okay? It won't rotate, okay? So in that case, so force along the direction of the distance. So the force along this direction, right? In that case, okay, maybe let me draw a diagram here. So this is the force acting on the rotational axis. And this is the force acting along the direction of the distance, like this. In this case, the reason it cannot produce rotation, I mean, we characterize it by the angle here. So when the force is going along this direction, there's no angle between the force and the distance. So theta equals 0. When theta equals 0, you have a sine theta equals 0, and therefore the torque equals 0. Okay? So in both cases, you have 0 torque. So therefore, you cannot produce a rotation. Okay. So, and that's the two cases. Your force is kind of ineffective. Okay. Now the other case, when you're acting at a certain distance from the rotation axis and the angle theta is not 0, certainly you can produce a rotation. Okay. So for the rest cases, you can produce a rotation with the force, because from this formula you have a finite torque. Okay. So other forces. So you have tau is not equal to 0. Okay. So you have a finite torque, and then you can rotate this thing. Okay. For example, in this case, right, if I apply force along the tangent direction, right, like this, I can rotate the torque, the lid. In the case of the door, you will apply force pushing the door like this. You look from the top, you have force pushing like this, right? Certainly it can rotate the door, right? As you understand from intuition. So we see that this definition here take into account of all different cases, okay, of the force. Okay, sometimes when the force produces 0 torque, this thing cannot be rotated. Sometimes when the force produces non-zero torque, this thing can be rotated. Okay, so this is actually appropriate for us to look at. This is the correct quantity to look at in the case of we want to talk about rotational equilibrium. Okay. Any questions so far? We're good? Give me a, okay, good. Now let's you guys, well, this quantity is new for us, but we had like a similar quantity like this one with similar definition, force, distance, trigonometry of an angle or something, you know. Do you guys remember what quantity we talked about kind of similar to torque? You can send me email. I mean, sorry, send me a message.
Now, baby.
It's work, right?
Work.
I think so. All right. Did you already get the plant stood up in the buckets or no?
Hannah, you may want to, okay, yeah. So remember, work is defined as force times distance times cosine theta, right? Well, in that case, we're kind of saying, we're taking into account how the impact of the force on the motion, whether it has a positive impact, negative impact, or 0 impact. Well, in that case, right, you have a force, and then you have a distance going of the motion, and then you have an angle. But in that case, it's the cosine of theta that matters, which is the component, which gives you the component force going along this direction of the motion. Okay. Well, in this case, which we have very similar quantity, but in this case, it's sine theta that matters. Okay. Now, why is that? Okay, it's kind of clear. So you can write this definition as F sine theta times D. What is this part? Okay, so this is nothing but the one component of the force. So if this is the angle of theta, right? So F sine theta is this component, okay? As we see here, right? And F cosine theta is this component, okay? Well, this component here is totally useless because it's going along the direction of, I mean, this distance. So it cannot produce any rotation. Well, this component is perpendicular to that direction. So this is the most effective one for rotation. Okay. So this makes it a little bit different from the concept of work. Okay. I don't want you guys to get confused about these two. They are not the same quantity by any means, but they're kind of a little bit similar in this sense that we're only one component of the force is effective. Okay. Now let's also talk about the units of the torque. Okay. Hold on. So according to this, right, you have force, which is in newtons, and distance, which is in meters. So unit for torque is actually Newton times meter. And accidentally, it is the same unit for the work, right? And we know in that case, we call this joules, right? Work and energy has unit of joules. Well, it turns out the torque has the same unit, but normally we don't call it joules here. We just leave it with Newton times meter. The reason for that is torque is not really a energy. It's a totally different quantity, okay? As I said before, normally when you have different quantities that have same units, they normally means that they're the same thing. Like in the case of work and energy, they're essentially the same thing. But this is the exception here, okay? Torque, although it has this unit like this, it is not the same as work or energy, okay? It is a totally different quantity. The reason that torque has the same unit is essentially, if you calculate work done by torque, you can write like a tau times theta. Well, this is a measure in radian, so it's not a real unit. So that turns out in this case, the torque has same units as work. Well, we don't use this in our calculation or anything, so you need to understand it. But basically, I just want to try to explain why they have the same unit, but they are not the same quantity, okay? And one thing you can see from it is torque is actually a vector. It's not a scalar, okay? It very naturally has a direction. For example, if you have let's say, you have a force like this, right? If you apply this force to this rod, you understand this whole thing will go counterclockwise, right? So make it go counterclockwise. And if you have a force like this, you understand if you only have this force, it's gonna make it go clockwise. So there's naturally a direction associated with the torque. Okay? So normally when we go counterclockwise, we say the torque is larger than 0. When we go clockwise, we say the torque is smaller than 0. So it could be positive or negative, depends on whether it makes it go counterclockwise or clockwise. Okay. Notice that this direction cannot be seen by this definition here. Okay. In either case, the definition always give you positive torque. Okay, because the angle here is only like a theta. Any angles between 1 and 0 and 180 will give you positive sign. So this is always going to be positive. This is only the magnitude. You have to put it by hand, the sign of the torque. Okay? There's a better way to define torque that you don't have to put it by hand, the sign, but that's again going beyond the scope of this class. You can define torque using cross product of two vectors, but that's too much for us, so we don't talk about that. So in this class, just keep in mind, there's only two possibilities. One is making the torque make it go counterclockwise. The other one, torque make it go clockwise. Okay, so and we define the sign correspondingly. Okay, and remember, work and energy are scalars, so they don't have signs. I mean, they don't have directions. So that separates them from each other. Okay. Any questions so far? Good. Okay. Okay, good. So let's then talk about our rotational equilibrium condition. Okay. So what we're saying here is we introduce the quantity tau to say that tau is the reason, torque is the reason for rotation. Okay. So for something not to rotate, then we need to require the total torque equals 0. Okay. That's going to be our rotational equilibrium condition. So we have totally 2 rotational equilibrium conditions. Okay. The first one is the previous one. We have total force equal to 0. The second one is what we just learned, total torque and e to the 0. Okay. The first one, make sure that the object does not move in a hole. The second one, make sure that the object does not rotate with respect to one part of it. Okay. So both of them are important for something that's in equilibrium. Okay. I think that's pretty natural to understand, right? So with this in mind, let's go back to our original problem of this balancing the pencil. Okay. Let me try to explain why you can balance the pencil by horizontally by putting the finger in the middle of it. Well, you cannot by putting it at one end of it. Okay. So let's consider the first case, okay? When you have a pencil, I'm gonna roughly say the pencil has a uniform mass distribution, so it's like a rod. Now let's, in the first case, let's say you put your finger right here underneath the pencil like this in the middle, okay? Let's see whether, why it can balance it, okay? Now we still need to start from the free body diagram and do force analysis. So there's two forces on the pencil. One is the normal force acting on the middle right here. Well, the other one is actually gravity, okay? So where does the gravity go? In principle, the gravity goes everywhere because there's a mass everywhere on the pencil. However, that's gonna make things really complicated. So in case of, to consider gravity, we use the idea called center of gravity or center mass. They're basically the same thing for us. Well, we can calculate this, we can define this concept really rigorously with mass, but we won't do that. So the common sense is just basically the center of gravity is like assume that everything's acting on, all the gravity is acting on the object at a single point, what that point will be, right? For a point, for a mass distribution like uniform, it's kind of common sense to say that most times it's the located center of okay, let's call it geometrical center. Okay. For us, for most cases, the center of gravity is just the geometrical center. For example, for a rod, it's going to be just at the middle. Okay. We will say it like this. Okay. We will say all the gravity is acting on the center of gravity, which is at the middle. Well, for a block, certainly it will be that like at the middle as well. For a sphere, is also going to be at the middle. And as we know, in the case of the Earth, we know that the attraction to an object on the Earth is equivalent to attraction to, as if all the mass is located at the center of the Earth, okay? So again, this is the center of gravity idea. Okay, anyway, so in this case, we use this idea, there's two forces on the, let me draw it again here. Two forces here. One is center of gravity, the gravity. The other one is normal force, okay? So, you can define this as a positive direction. Let's try to set up, see whether this can be satisfied, okay? Total force, okay? You can calculate total force, you can N minus mg equals 0, okay? So in order for the total force to be 0, that means N has to be equal to mg. So the normal force you provide here at the middle has to equal to mg. What about the torque, okay? Well, in this case, total torque is 0. So you need to calculate torque by each one of them, right? Remember, torque is defined as Fd times sine theta. So this distance here refers to the distance between the acting point of the force and the rotational axis. So in order to calculate torque, you have to define a rotational axis, okay? So what is the rotational axis? It turns out that, okay, in this case, there's nothing is pinned. No point is pinned, right, for the pencil. So it turns out that you can choose any points you want as your rotational axis. So let's choose it at the middle for here. So if you choose this as a rotational axis, the torque given by normal force is simply 0 because there's no distance. Same thing, the torque given by gravity is 0 as well. Certainly the total torque is 0, okay? So this condition is satisfied. So both conditions satisfied if you have N equal to mg. That means this rod can stay in balance or stay in equilibrium, rotational equilibrium, when you have a finger underneath it at the middle, okay? Now let's look at another case, okay? In this case, let's say you put a finger on one end of it, okay? You put a finger right here, okay? That means the forces you have are gonna be normal force going at this point, going up, while the gravity going down, like here, okay? So you have this kind of a free body diagram. It's a little bit different from this, okay? So again, try the first equilibrium condition. So you have N minus mg, that's the total force, equal to 0. That gives you N equal to mg. So in this case, in order to balance it, you still require N equal to mg, okay? But let's try the second condition here. Okay, again, when you calculate the torque given by each of the forces and then add them together. So let's choose our rotational axis to be here, okay? If that's the case, then torque given by normal force is 0 because D equals 0 here. But we have torque given by gravity, right? So tau G, let's calculate tau G, okay? According to our formula, it is gonna be FD sine theta. So F is the force, you have mg here. And then D here is just the distance from here to here. So this is half of the length of the rod. If this rod together is length L. And then times sine theta. Well, theta is the angle between this distance and this distance. So it's going to be 90 degrees, okay? And remember, this is only the magnitude. Okay, now if you look at the direction, right? So this torque, this force make it go clockwise. So it should be negative. Again, you put the sign by hand, okay? So together you have a negative mg L over 2. This sine 90 is just 1. So you have this torque here. This is negative torque. So the total torque here is, if you add them together, tau m plus tau g is going to be negative mg L over 2. Well, certainly that's not 0. So this cannot be satisfied. So you cannot have equilibrium, rotational equilibrium. So actually, because of non-zero torque, the whole thing will go rotate like this, okay? As predicted here, okay? Now you may wonder, what if I choose a different rotational axis? It turns out that a different rotational axis is going to give you the same thing. Let's say this case and this case. Let's say I choose this one as my rotational axis. I call it O prime, okay? In this case, the torque given by gravity is 0 because it crosses the rotational axis, but torque given by normal force is not 0. So if you calculate, it's equal to the normal force times the distance, which is again L over 2, times the sine, again 90 degree, because they're perpendicular, this torque perpendicular. Well, what about the sine? So if this is your rotational axis, right, this normal force is going to make it go this way. So it's again negative, okay? Now if you plug in n equal to mg, so you got negative mg L over 2, okay? So it's the same as the previous case. So the total, okay, so the total torque here is again tau m plus tau g, which is negative mg L over 2. As you see here, both cases, they have the same amount of torque and this negative. So it's not 0, and it's gonna make it go clockwise, okay? Make the whole thing rotate clockwise. So it doesn't matter which rotational axis you choose. As far as you put your finger on one end of the rod, it's gonna rotate like this, okay? You cannot stop rotating unless you put the finger at the middle, okay? Okay, does that make sense to you guys? Any questions? Good, okay. We have 10 minutes left. Let's see, maybe let me show you one example in the book. I'll show you kind of quickly. And I'm running out of the room here, so I'm gonna just use this to show you, okay? Let me go all the way to, I wanna do the seesaw problem, you know, because that's the kind of easy, okay? Yeah, basically we skipped all 8.2, the center mass thing. We're just saying that the center mass at a geometrical center for simple objects. So let's do the seesaw problem here. Example 8.8. Yeah. I'm gonna just talk about it using the lecture page. Using the book, okay? So what do you have here? You have two people sitting next to sitting two different sides of the seesaw, okay? And the seesaw itself has some weight, and each person has a weight as well, okay? Now the question you want to see here is, okay, there's a woman weighs 55 kilogram, and sitting at the whole seesaw is with length L is given as 4, and then compute the torque of the seesaw passing the pivot point like here, and then the man. Okay, so basically the question is, if the woman sitting at the end, where should the man sit where the man has a bigger mass, 75 kilogram? Where should the man sit? I mean, it's called X here. What should X equal to in order to balance the seesaw, right? That's a key question, okay? It also asks you about the normal force exerted by the pivot point at here, okay? So for this purpose, we need to do free body diagram, force analysis to the seesaw, okay? there's essentially four forces here. One is the gravity of the seesaw acting on at the center of gravity at the middle. And then there's a normal force given by the pivot point right here. There's also two normal force given by these two people. Basically, they're the weight of these two people. So they simply are drawn as two weights. So there are these four forces here, okay, acting on it. And then we can use the two equilibrium conditions. So one condition of this is saying that basically all these four forces, if you add the torques together, the torque with the four forces together, it should be zero. That's the total torque equals zero condition, okay, like this one. And well, two of them have zero torque because they cross the rotational axis. Okay, you define, I mean, it's kind of convenient to define rotational axis at the pivot point because that's very natural point choice for rotational axis. And it's convenient because two torques become zero. You can define any other points as a rotational axis, but if you define some other point, you need to calculate all these four torques, which is going to make your work more, you know. So anyway, if you choose this axis, rotational axis, this two does not give you any torque, so they're 0, 0, like right here. And then you have a torque given by the man, and then torque given by the woman. So the torque given by man is equal to the mass weight of the man, the force times distance, which is x, right? So mgx force times sine theta, where in this case theta is again 90 degrees. So sine theta is 1. Notice this is negative because this man make it go, the force make it go clockwise, so it's negative. You put it by hand. Well, for the woman here, is equal to force, which is the weight mg times the distance, which is L over 2, distance from here to here, times sine theta. Again, theta is 90, sine theta is 1. And it's positive because this torque make it go counterclockwise. So in the end of the day, we only have these two torques, okay? And they balance each other. From there, we can solve for x is equal to m, I mean, the g cancel out. So it's ml over 2 divided by capital M. And we got 1.47 meter for this distance. So the man has to sit like 1.47 meter away from the middle. Okay. Well, what about the force on here? Well, you can use the total force equal to 0, the second equilibrium condition, the other equilibrium condition to do that. Okay. So you have four forces on the balance, 3 of them going down, 1 going up. So 3 negative ones plus 1 positive ones equal to 0. And then from there, you got n equals to, I mean, you can solve for n by basically adding all these 3 weight together, you got this number here, okay? Does that make sense to you guys? Good, okay. Now, part C, you can look at, it's the same, repeat the same thing, but compute the torque using the rotational axis on the left end, okay? You can see, as you can see here, if you use the left hand here, one of the force, which is the women's weight, will not contribute because it's across the rotational axis. But you have 3 torques, like 1, 2, and 3, and then if you compute them correspondingly, you again get the same x, and then it's same value as the previous one. Okay, except some rounding errors here. It's the same. Okay, so I guess this finished what I want to talk about today. So, and this is basically the physics I want you guys to learn from chapter 8. Again, this is only one piece, right? This is just the balancing of torque. So just this one piece. So you should be able to do your homework on this chapter, or you can wait until tomorrow. In tomorrow's lecture, we'll talk about, we'll give more examples about the rotational equilibrium, and we'll also do some exercise together about the rotational equilibrium, okay? Basically, it's a balancing of torques, okay, for this chapter.